In this lesson, we're going to see how we can solve Coulomb's law problems using the KUESS system for problem solving. We'll take a look at the Coulomb's law equation and the variables that are in it. We'll review how to set up Q's, and then we'll look at 3 practice problems, one where we'll solve for the electrical force, one where we'll solve for the charge, and one where we will solve for the distance. You've seen the Coulomb's law equation before. There's several parts to it. The electric force is represented here by the letter F, and it's measured in newtons. The charges of object 1 and object 2 are represented by the letter Q, lowercase q, and those are measured in coulombs. And the unit Coulomb is abbreviated with a capital C. The distance between object 1 and object 2 is represented by the letter R for radius, and the radius is measured in meters. And the letter K, lowercase k, is a proportionality constant called the Coulomb constant. It's always the same in this equation, and its value is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Let's briefly review scientific notation, since we'll need to use it in this lesson. Anytime a number is written in scientific notation, there are 3 parts. The first is a number greater than 1 and smaller than 10. The second part of the number is the part that says times 10. That lets us know that we're working in scientific notation. The third part of the number is the exponent. That tells us how many places we're moving the decimal point for the number. The exponent can be positive or negative. When it's positive, we're dealing with a number larger than 1. And when it's negative, we're dealing with a number smaller than 1. Scientific notation is a very useful way of writing really big and really small numbers, and we have a lot of those in physics. Let's expand these into standard decimal notation and see what numbers they represent. First, we have the 8.99, but the exponent of 9 tells us we need to move the decimal point 9 places to the right. So we moved it 1, 2, 3, 4, 5, 6, 7, 8, 9 places. And we can see that this 8.99 times 10 to the 9th is really 8,990,000,000, which is a really big number. Looking at the number on the bottom of the screen, we see that it has a negative exponent, so we know it's a number less than 1. We know that we're going to need to move the decimal point 11 places to the left. Let's start with our number 667, and we're going to move the decimal point 11 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wow, that's a lot of zeros. You can see why it's more convenient to write these numbers in scientific notation. It's also a lot easier to avoid making mistakes. When you're putting a number in your calculator in scientific notation, you don't put in the times 10 part. What you do for the top number, and this example uses the Google calculator that you may be using on your Chromebook, you put in the first part of the number, so you would press 8.99, and then instead of doing times 10, you're going to push the key that says EXP for exponent. If you're using your own calculator, it might say E or EE on your calculator. But on the Google calculator, it says EXP, so you'll push that, and it will add the E on the screen up here. That the E means the same thing as the times 10. And then you will put in the exponent, which is 9. So you push the 9 key. And you will have 8.99E9 on your calculator screen. And if you hit equals, it will give you that broken down into standard decimal notation, 8,990,000,000. Now, if you're doing a number with a negative exponent, it's a similar process. On the bottom of the screen is the Google calculator with the second number entered. You press 6.67. You don't put times 10, you push the EXP key, or E or EE, depending on your calculator, and then you're going to put in the negative 11. On the Google calculator, you'll do that by pushing -1, 1. On most calculators, if you're using your own, they'll have a positive and negative button instead of the minus key, so you would push positive, negative, and then put in 11. We're going to be using the KUESS system to solve these problems. So to quickly review, the K is for the knowns. That's the values you get from the problem. The U is for the unknown, which is what you're trying to find. The E is for the equation. What equation are you going to be using? In this case, it'll be the Coulomb's law equation. S is for substitute, which is where you plug in the known values into the equation. And then you solve, showing each step of your work. These problems have some large numbers in them. So instead of handwriting them, I went ahead and typed out the solutions so you can read them easily. But let's go through each one. For this first problem, two objects have charges of positive 0.00054 coulombs and negative 0.00028 coulombs. They're separated by a distance of 1.25 meters. What is the electric force between them, and is the force repulsive or attractive? So we have several pieces of information to look at. In the knowns, we can put in our two charges of our objects, the 0.00054 and 0.00028. The first one's positive, the second one's negative. We can put in the distance, which is 1.25 meters. We can write down Coulomb's constant. It's not given in the problem, but because it's a constant, it's always the same, and we know we're going to use it. So that's going to be 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And we know from the problem that we're solving for the force between the two objects. The Coulomb's law equation is written in the equation section. Force equals K times Q1 times Q2 divided by R squared. So I'm going to substitute each number in where it goes. And we can see right here, we have Coulomb's constant, the 8.99 times 10 to the 9th in place of the K. We have 0.0054 in place of Q1 and 0.00028 coulombs in place of Q2. Now you notice I did not include the positive and negative signs here, and that was on purpose. It's not a mistake. You can do this problem including the signs as you work your way through, but it makes the math more complicated. It's much simpler just to look at the signs and decide at the end whether it's repulsive or attractive. We know that if the charges are the same, they repel, and if the charges are different, they will attract. In this case, we have one positive charge and one negative charge. So at the end, we're going to be able to say that the charges attract because they're opposite, without actually having to keep track of the positives and negatives all the way through the problem. Okay, continuing on the bottom of the fraction, we have R, 1.25 meters, and that whole thing is going to be squared. So I put it inside parentheses and put the exponent on the outside to tell me that I'm squaring the number and the units. From here, we're just going to do some arithmetic and simplify it down. The first step is to multiply together 8.99 times 10 to the 9th times 0.00054 times 0.00028, and that gives me this number right here, 1359.288 Newton meters squared. If you look at the units, you can see that the Coulomb's constant was Newton meters squared per Coulomb squared, and we multiplied that times Coulomb once times Coulomb twice. So it canceled out the Coulomb squared on the bottom part of the unit and left just Newton meters squared. The second step in simplifying is to take the 1.25 meters and square it. That gives us the 1.5625 meters squared on the bottom of the fraction. Take your calculator and divide those two numbers, and you will find that the electric force between the two objects is 8.69.9 newtons. Remember, forces are always in newtons, but you also can tell because in the problem, the units were Newton meters squared divided by meters squared. So the meters squared are going to cancel out and leave just newtons. The second part of our answer is that we know the force is attractive between the objects because the charges are opposite. Back in the beginning, we had one positive and one negative charge, so we know they'll be attracted. Let's look at a problem where we need to solve for charge. In problem number 2, we have an object with a charge of negative 6.7 times 10 to the negative 6 coulombs, and it's located 0.84 meters away from a second object. The objects are repelled from each other with a force of 4.78 newtons, and we want to find what is the electric charge of the second object. Taking the known values from the problem, we have Q1, the charge of the first object. We have F, the force between the two objects. We have R, which is the distance between the two objects. And we have the Coulomb constant, which isn't given in the problem, but we know it's always 8.99 times 10 to the 9th. Our unknown in this problem is the charge of the second object, or Q2. We're going to use the Coulomb's law equation, F equals K times Q1 times Q2 over R squared. And we're going to start out by substituting all of the known values in. We know F is 4.78 newtons. We know K is 8.99 times 10 to the 9th. We know Q1 is 6.7 times 10 to the negative 6 coulombs. Q2, we're just going to put Q2 because that's our unknown. And then the distance is 0.84 meters squared. And again, I put that inside the parentheses so that I know I need to square the number and the unit. We can start by simplifying some of the numbers. The first thing I did is to multiply together 8.99 times 10 to the 9th and 6.7 times 10 to the negative 6th, and that gave me 6.02 times 10 to the 4th Newton meters squared per Coulomb, right there. And then the second thing I did was to square the distance, 0.84 meters. I square it, I get 0.70 meters squared. For the next step, we're going to start isolating our variable, Q2. First thing I wanted to do was get rid of the fraction, so I multiplied both sides of the equation by 0.70 meters squared. And you can see on the right-hand side, the 0.70 meters squared canceled out on the top and the bottom. Next, I simplified by multiplying the 4.78 Newton force times the 0.70 meters squared, and I got 3.3 Newton meters squared. Now I can take another step toward isolating Q2. So I divided both sides of the equation by the 6.02 times 10 to the negative 4th Newton meters squared per Coulomb. I divided both sides of the equation by that value, and we can see that on this side it cancels out and we're left with just Q2. After we cancel out those numbers, we're left with Q2 equals 3.35 divided by 6.02 times 10 to the 4th. If you put that in your calculator and do the division, you'll find that Q2 is going to equal 5.57 times 10 to the negative 5th coulombs. And that's going to be a negative number, not because we did the math, but because we know from the problem that the force was repelling the two objects, so the charges have to be the same. Q1 was negative 6.7 times 10 to the negative 6th, so Q2 has to be negative 5.57 times 10 to the negative 5th. In our third example problem, we're going to be solving for distance. In this problem, we have two objects with charges of positive 2.5 times 10 to the negative 5th coulombs and positive 4.6 times 10 to the negative 6 coulombs. And these two charges are repelled by a force of 0.527 newtons. And we want to find what the distance is between the objects and whether the force is repulsive or whether it's attractive. Now, we can tell right away that the force is going to be repulsive because both of the charges are positive. So that's the easy part. Let's work on the distance. In our knowns, we have Q1 plus 2.5 times 10 to the negative fifth. We have Q2 is plus 4.6 times 10 to the negative 6 coulombs. We have the force, which is 0.527 newtons, and we have our Coulomb constant, 8.99 times 10 to the ninth. Our unknown this time is distance, so it's going to be r, lowercase r. Our equation is still the Coulomb's law equation, F equals K times Q1 times Q2 divided by r squared. We can begin by substituting all of the known values into the equation. So we substitute in the 0.527 Newton force. We can substitute in the 8.99 times 10 to the ninth Coulomb constant. We can substitute in our Q1 and Q2 values of 2.5 times 10 to the negative fifth and 4.6 times 10 to the negative sixth. These both happen to be positive, so I don't need to show anything special for the sign. But remember, if I had a positive and a negative or two negatives, I would not include the signs here because I'm going to apply the positive or negative at the end based on whether they're repelling or attracting. I'm going to start by simplifying the problem as much as I can. If I multiply 8.99 times 10 to the ninth times 2.5 times 10 to the negative fifth times 4.6 times 10 to the negative sixth, I will get 1.034. And if you look at the units, we multiplied Newton meters squared per Coulomb squared times coulombs, so all of the coulombs cancel out and we're left with a unit of Newton meters squared. For our next step, we need to get the r, our unknown, off of the bottom of the fraction and get it isolated on one side of the equation. I'm sort of combining two steps here. I multiplied both sides of the equation by r squared divided by 0.527 newtons. You could do that in two steps and multiply both sides by r squared and then divide both sides by 0.527 newtons, but I did them together in one step just to speed things up a little bit. On the left side of the equation, you see that 0.527 newtons cancels out in the equation, and on the right side, you see that r squared cancels out. After canceling everything out, we can see that we're left with r squared equals 1.034 Newton meters squared divided by 0.527 newtons. If you put that in your calculator, you'll find that r squared equals 1.962 meters squared. The last thing we have to do is unsquare the r. We have r squared, but we're trying to find r. So we're going to do that by doing a square root on both sides of the equation. Your calculator has a button with the square root sign on it. The square root of r squared is r. The square root of 1.962 is 1.4. And the square root of meters squared is meters. So we see that the distance between the two objects is 1.4 meters. In this lesson, we've looked at the Coulomb's law equation and the different variables that make it up. We've reviewed scientific notation and how to set up cues for the Coulomb's law problems. We have solved Coulomb's law problems for electric force, for charge, and for distance.